So Graeme from All Souls in Oxford, and will speak to us about the Virasoro algebra, its roles and its strangeness. So, welcome.
Well, like Ed, I have to express lots of gratitude to Peter. I was never a collaborator in quite the same kind of way. I came upon Peter when I was trying to change from being an algebraic topologist to someone who was interested in quantum field theory. And Peter was the person, first of all, who pointed out to me the structure of the world of physics, told me which people I should take notice of, which people were worth listening to, but also encouraged me in lots of ways. When I came to Cambridge, I would never have survived without being looked after by Peter. Well, this isn't the place to tell you lots of examples of how that happened, but it was very, very real, and I'm very, very grateful. I actually also ought to apologize. As I said in the synopsis of the abstract of what I was going to say, that everything Peter did was connected with the Virasoro algebra. That's completely false, as you heard from the preceding talk. What may be true is that all the papers of Peter's, which I've actually sort of looked at very carefully, have something to do with the Virasoro algebra. That's a rather different thing, and so I apologize for that. Well, nevertheless, I'm going to begin more or less from the same point as the last talk did. In 1972, let's look at my watch. In 1972, Peter wrote two papers. I think he wrote a lot more than two papers, but there are two papers that I was very aware of. The first was, I've had them all. There's nothing to write.
Chalk is here.
Oh. So in 1972, there were two very notable papers. The first was especially notable to me in that I didn't know the meaning of almost any of the words in the title. It was called Compatibility of the Dual Pomeron with unitarity. Well, it goes on, that's enough for the moment. It goes on to say, and the no-ghost theory for the something or other. Well, I knew what compatibility and unitarity meant, but I didn't know what any of the other words in the title meant. And to be perfectly honest, I still don't. I don't know whether pomerons are things which they find at CERN, or perhaps not. But this was the famous paper, as we heard, in which Peter discussed this dual model, and by exploring the representations, by studying and finding out things about the representations of the Virasoro algebra, which was meant to be a symmetry algebra of this model, he showed that it was only possible to construct it in 26-dimensional space-time, Minkowskian space-time. Well, that of course was in some ways a big blow to string theory, because people laughed, of course, at first. And the other paper was the one that I sort of felt I understood much more, which was about, I think I won't bother to write out the title, which is also fairly long, but it's about the quantum dynamics of a relativistic string. So it at least was geometrical. One considered some piece of string moving in space-time, and one wrote down the equations of motion and tried to study them like an ordinary quantum mechanical problem. In that paper, that was of course about open strings. I tend to prefer to think about closed strings, which is simpler, because if you talk about open strings, you have to have the boundary condition. The ends have to be moving at the speed of light and so on. So it's somehow simpler if you're a pure mathematician to think about closed strings, which are circles. Well, I didn't think very much about this paper because it was, you see, between these two papers, so the other one was, I'll just write down quantization of a massless string. Now, the important thing is that there's a kind of paradigm shift between these two, because this was, although they both, in some sense, use the same mathematics, the representation theory of the Virasoro algebra, the Virasoro algebra, which I imagined in those days that Virasoro was some prehistoric Italian mathematician who had discovered the circle. But in fact, he's someone about the same age as me, and he had discovered this symmetry group, and had nothing seems to have been, at least in the first instance, further from his thoughts than that it was the group of diffeomorphisms of the circle. Although, in the same year, 1972, of course, everyone started thinking of it that way. Now, the reason why one should be interested in this paper, I think, is that it gives great hope to a certain point of view on what one could, or hope of what one could do in physics. I mean, if one wants to have some theory of gravity, people, I think, nowadays all believe that in some way one has to make the space-time manifold emerge from the theory. Well, what does that mean, emerge from the theory? Emerge from what exactly? Well, presumably it means it's got to emerge from some kind of algebraic structure. And the Virasoro algebra, which Virasoro introduced, I think, in 1970 for the first time, so only 2 years, but actually only, I think I looked to see it was 18 months before this paper was submitted. This algebra is defined by means of generators and relations. It's just a very simple algebraic device which you can write down in a line or so. And yet, when you understand it, well, you first of all see that it's the Lie algebra of the group of diffeomorphisms of a circle with a central extension. The central extension is crucial, and I'll be saying more about that in a moment. But then, by exploring more and more of this representation theory, you find, first of all, that in this algebra, and it's the things you get out of it, you find an almost complete account of the geometry and the topology of surfaces. That is a most remarkable thing, and you even find out things about three manifolds. So it's something, I mean, you could hope at least that that was an enormous breakthrough, just that simple fact that from a simple algebraic structure you get all this really genuine geometry. On the other hand, to this paper, which to me was the accessible one and seemed like something I could understand, in a certain sense that perhaps tells the opposite story, because this paper introduced well, you see, in this paper, one thought of a string moving along some world sheet contained in space-time. So this was a two-dimensional thing, the sheet swept up by the string as it moves in time. And all of this that I was just telling you about pertains to the geometry of this. And it isn't very directly telling you anything about the geometry of space-time. So another point of view on what string theory is doing is that string theory is just telling you some kind of algebraic, well, in the high noon of string theory, I suppose, when people thought that, well, I don't know what people, haven't kept up with string theory at all, I don't know what currently people think. But in the high noon of the theory, people thought that when you had a Riemannian or pseudo-Riemannian manifold, you could associate to those things two-dimensional quantum field theories. And the remarkable thing was that these things, possibly with some structures, like bundles on them, or whatever, sort of bells and whistles that you attach to these things, that this is pretty much an equivalence. And the problem of gravity, which is that if you start trying to think of a, say, a three-manifold with a Riemannian manifold with a Riemannian metric, trying to evolve according to Einstein's equations, that means you're looking at it moving along the gradient lines of the Einstein action, the integral of the scalar curvature. Then this is a problem which is very, very badly posed from the point of view of geometry. It's a problem where the downwards, if you thought of it as a variational problem, if you start trying to go down the trajectories of the flow, then the manifold just disintegrates, it shreds itself into ribbons and that kind of thing. So that's not very satisfactory. This was something close to being, it was hoped, an equivalence, but these things were much more tractable, so that one hoped that by doing, by working with in this larger sphere of two-dimensional field theories, one would somehow break the problems of this bad posedness of the variational problem for gravity. In fact, it was better than that. One could say something more precise, and I should mention the famous theorem of Topological in this. So we have, I said, we have this symmetry algebra in string theory, which is more or less the diffeomorphisms of an interval or of a circle. But it's very important that it arises because it arises with a central extension, and the central extension is there because of positivity of energy, essentially. Well, you can classify very easily the central extensions of this Lie algebra that we are interested in, and they're classified by a positive number, usually called the central charge. The central charge of the theory. Now, the theory that arises. But the central charge, in fact, is something, although it arises here as classifying the representation, the central extension of the Virasoro algebra, it's a very general thing which can be defined for any quantum field theory. If you think of a quantum field theory as when you take some space-time manifold, and suppose we, for the moment, would rotate it so that it's Riemannian. And so suppose we have a compact Riemannian manifold, M, then a theory will have a partition function on that. And the central charge you can define in the following way. You take, supposing our theory is a theory of d-dimensional manifolds, then supposing we do it for a d-dimensional sphere, and we want to give it a Riemannian metric, so let's give it radius r. Well, if we take the logarithmic derivative of that, and r equals 1, that precisely is this central charge. So this this tells you, you see, that it's about something about how the theory responds to manifolds getting bigger and bigger, how the partition function, the growth of the partition function. On the other hand, in the original examples where it was used, it classified the central extension of the Diffeomorphism group. In fact, it's quite, this dual role of this central extension, this C, is quite interesting in itself, in that it's an interesting, this central extension, on the one hand, is to do with commutation relations of ordinary quantum mechanics. So that's the way it arises in this second paper of Friedman's of 1972. But in the first paper, getting rid of the ghosts in this theory of the dual Pomeron, whatever that may have been, was all to do with counting the number of states that a string moving in 26 or however many dimensions would have, and seeing that when you took the symmetry conditions coming from this Virasoro algebra into account in the proper way, you only had a number of degrees of freedom as if the string were moving in 24 dimensions, 2 dimensions lower. And so this C always has a kind of ambiguous dual role between an entropic interpretation where you're counting how many states there are around, and on the other one, this thing coming from the commutation relations of essentially basic quantum mechanics. Sorry, I'm very happy to be interrupted if anyone wants to interrupt me, because I happily or otherwise, I only got a list of the people who were expected to come to this meeting late yesterday. I think I might have just given up completely in despair if I got earlier, because of having so little idea quite who I was really expecting to be talking to. Anyway, I apologize for I started trying to recalibrate my talk and so on, but well, anyway, let's go back a bit in time.
If you really don't mind interruptions.
Sorry, yeah.
Do you really think of that arrow as an equivalence on it?
No, I mean, you see, I put and structures. But, so it would be very interesting, I mean, when I first got into this, I thought, well, you know, these physicists, they don't know any mathematics, I thought. This is completely wrong, but I was very young and very foolish. And I thought, well, the trouble is they don't have a proper definition of what quantum field theory is, and if one sorts out a few of these things and just makes things a bit clearer, then you'll be able to make a nice theorem like this. And of course, well, I'm afraid all one can say about that is that I was young and foolish. I wasn't all that young, actually, but I was trying to get out of algebraic topology at the time, and I hadn't thought much about physics. And in fact, what the last thing I hope to get to in this talk will be an example of how physicists do things a lot better than mathematicians, or a lot more clearly. Let me now, with a slight jolt, change a little bit, and I wanted to just talk a little bit about this group of diffeomorphisms of the circle. So we always imagine it's orientable, and this always means the orientation of the preserving ones. Now, it's closely related to something which is nearly a group, but not quite. Supposing V is the usual closed disk in the complex plane, and supposing you consider the embeddings, the holomorphic embeddings of this in its own interior. So we take the disk and we take a map, well, we take a map from the disk to the disk, let's say, which embeds this somehow in the interior. So you can imagine forming an annulus like that. So we take this and we put it in there. Well, this is a semi-group, not a group. But on the other hand, you can see pretty clearly that in some sense you could pretty much, these are all in some way invertible maps where they're defined. So it's very close to being a group. These two things are this semi-group, and these are holomorphic embeddings. So for instance, if this was surjective, then we know that it has to be a Möbius transformation. It has to be an element of SL2C or SU11. Now these two things, however, are related in a way that makes this look more, they're related, so to speak, in the way that the upper triangular complex matrices are related to the unitary group, you might say. In the right way to think of it is that if you have a diffeomorphism of the circle, you can use it to attach two disks together along their boundary and make some kind of sphere. Now, but there's only one kind of sphere it will have a conformal structure when you sew these things together. So all spheres with conformal structures are the same up to a Möbius transformation. So if you do this, you make a sphere, a version of the Riemann sphere, in which the sewing together will happen along some sort of complicated surface roughly running around the equator. But of course, you can then, below this, you have a disk, and by the Riemann mapping theorem, you can straighten that out. It has a unique up to a Möbius transformation equivalence to the ordinary unit disk, but so does the disk above it. So what you are really doing when you sew these things together and apply the Riemann theorem twice is write the original diffeomorphism, roughly speaking, as something which is holomorphic on one side of the disk and holomorphic on the other. Now, you see, you can't, that's obviously not literally true. You can't, if you have a map from the circle to the circle, it's absolutely impossible that it extends holomorphically inside the disk. But it does, you don't have a Birkhoff theorem in the way that you do for a loop, say, in the general linear group, where you can factorize it into two different loops, one holomorphic inside the disk and the other holomorphic outside. It's a bit slightly more subtle than that. But effectively, you have a version of that same result. So these two things, these two groups are very, very closely intertwined. And of course, they're roughly speaking the same size, because this being holomorphic, this being one-dimensional, this is like half the complexification of that. As I said, if you think of this as being like the unitary group, this is like the upper triangular complex matrices. They're the same size. Well, anyway, this was very much studied early in the 20th century, and the person who's become my mathematical hero, rather, is Carl Loewner, who studied this in 1923 when he was trying to prove Bieberbach's conjecture. Bieberbach's conjecture is that if you have a holomorphic map from the complex numbers to itself, which takes the origin to the origin, and you might as well normalize it so it has derivative 1 there. So it will have some power series expansion as the origin. Then Bieberbach's conjecture is that if this is an embedding, a one-to-one map, holomorphic map, from the unit disk into the complex plane, then that implies that the size of the kth coefficient is less than or equal to k. That's best possible because the map z goes to z over 1 minus z squared is exactly in which those bounds are obtained. Well, in 1923, Bieberbach had already proved the case k equals 2, and in the paper I'm talking about, Loewner proves the case k equals 3. And of course, much later it was proved completely. But I want to say why a string theorist might be a little bit interested in this. Well, Loewner, very early on for his time, really, decided that one should think of this thing as essentially, this group, as essentially a Lie group with a Lie algebra. You see, if you start with the identity embedding the disk in itself, then if you want to move inside the group, you have to move along an inward pointing vector field. And if it's going to stay in the group, this will have to be a holomorphic. It'll have to be real analytic. It will have to be holomorphic for a little way as it goes in. So Loewner started studying it in this way, but he didn't quite study this. He removed that condition. Because he wanted to think of it very much as a group. And so he thought he should study the one-parameter subgroups in this, well, it's still a semigroup, I'm afraid. And what did he find? He found that there's a very interesting class of one-parameter subgroups of this, which the center of the disk, which do the following. Suppose you take any curve that starts on the boundary and moves around, doesn't meet the origin, and then just stops somewhere. Well, supposing you delete this curve from the disk, then clearly you have something which topologically is still an open disk, so you can apply the Riemann mapping theorem, and you'll get a diffeomorphism, a holomorphic map from the disk to itself, which maps the whole disk onto the complement of this curve, it's called a slit domain, a thing of this kind. Well, Loewner observed that these things are, if you just imagine this thing as growing from a little tiny bit here, and you imagine it getting bigger and bigger and bigger, and the Riemann map mapping with it, he observed that this is a one-parameter subgroup in the semigroup we're talking about. And furthermore, that these one-parameter subgroups are dense in, well, in a certain sense, the convex hull of them is the complete group. But these slit domains are dense in all the things like this. And he gave a two-line argument for that, and he refers for more details to an earlier paper by, I can't remember now, sorry. But he says the proof is essentially the following. And several times I've thought about this, and I think to myself, well, I completely understand why this is obvious. Suppose you have something in the domain where you embed the disk in its own center like that. And you'd like to say that this domain is very nearly a disk domain, as a slit domain. Well, you take an arbitrary point up here, and you make the following slit. You go down to there any way you like, to some point on the boundary. Then you go round until you very nearly get back, and then you stop. So that's your slit. Now, so he waves his hand and says, it's obvious that this slit domain is, if you look at it in any compact region, is an exact approximation to the one you really wanted, which didn't have a slit there. Now, I thought about this quite a lot, and sometimes I think I can see it and see that it's sort of obvious, and sometimes it seems extremely unobvious, and I can't understand it at all. But why might you be interested in this if you're a string theorist? Well, one of the things people, so we have, Loewner is interested in this exponential map. We have functions on the circle, which is a Lie algebra, and we exponentiate them, and in particular we exponentiate, so what would the vector field that you exponentiated to get this be? Well, you see, it has to take the points on the boundary into the boundary somehow, so it has to have a parting point along there, and send all the boundary here, and then squeeze it into this hole. So it's a pretty strange thing. It's a function that... well, anyway, he said there's an exponential map. And what Loewner didn't observe, but what was eventually found was that if you, just on the vector space, which is the Lie algebra, put an obvious Gaussian measure, then you get the measure on these curves, which in a different language you can call self-avoiding walks. You see, the one thing, apart from not hitting the origin, the thing they mustn't do is hit each other. So you get a measure on the self-avoiding walks, and that's what's now called the stochastic Loewner evolution, or the Schramm-Loewner evolution. And string theorists know that one of the main things people use two-dimensional conformal field theories nowadays for is to study percolation. And that is exactly this fact about the exponential map, that if you think of these as paths of water percolating into a disk, the measure on the percolation is precisely this exponential map. And anyway, I recommend Loewner's very short paper to you. I'm going to change gear just very quickly. I'm not being very well organized. So Peter himself, I noticed on his summary of himself on the Princeton website, listed his two main achievements, I think, the 26-dimensionality one, which we've all been referring to, and the other thing is what's always called the GKO construction, Goddard, Kenton, Olive. And I'd just like to say a tiny bit about that before I end. I meant to end at 3:30, am I?
Well, sort of, yeah. Slightly later.
Sorry?
Let's say 10 minutes.
Okay, yeah, okay, I won't do more than that. So what was that all about? Well, Peter's work on these early string theory models was all about understanding the representation theory of the Virasoro algebra. And in some sense, that problem was completely solved. Well, that problem was completely solved, not for unitary representations, however, by Fagan and Frenkel, Fagan and Fuchs, who completely classified the positive energy. I haven't even representations of Virasoro algebra. Then there were other people, Friedan, Shu, and Shankar, who determined the unitary implications of this. So this was all representations, not necessarily unitary. Then there was further work done which singled out the unitary ones, and that there was a fairly simple series of these. On the other hand, the representations weren't constructed. And the proof that they all could be constructed in a fairly simple and straightforward way was given by Goddard, Kent, and Olive in a very influential paper. And I'd just like to say a few words about that, because it again contains a very puzzling point, which I think is still not properly understood. The usual way in which people found representations of the Virasoro algebra was to take some compact group, G, and look at its loop group, the group of smooth maps of the circle into that, and to take some irreducible representation on some space H. And, of course, the diffeomorphisms of the circle act on this as a group of outer automorphisms, because if we're looking at maps from the circle into G, we can compose them with maps from the circle to the circle. So this is an outer automorphism group of that. And in the situation that we have, it automatically acts on this. Now, if it's going to act, and if this is an irreducible representation, it isn't going to have much choice of how to act because of Schur's lemma. But it still has some choice. But the surprising, so this way we can create all kinds, because we understand the representations of loop groups very well, we have a big supply of representations of diff S1. But that doesn't give all of the representations of diff S1, not even all of the unitary ones, all the unitary positive energy ones. And the interesting thing is that there's a formula in loop group theory, or if you like in physics, the Sugawara formula, which tells you precisely how to construct the representation of this on here from the loop group representation. It's an absolutely concrete formula which constructs the one from the other. In other words, essentially, the Lie algebra of this is contained in the universal enveloping algebra of the Lie algebra of this by a formula. So that means, supposing you take a loop group and say take a subgroup H of G and consider that inclusion. We'll take our irreducible representation here, regard it as a representation of this, and we can decompose it. It decomposes because the theory of loop group representations is so simple. It decomposes into irreducible representations of this group. So alpha is running through the irreducible representations of this, tensored with a multiplicity space. Let's just call that V alpha. This is just a vector space which tells you how many times this is contained in that. Well, now, because of this remarkable fact, we have diff S1 acting here and diff S1 acting here. But those things usually aren't very clearly related to each other. And what the Goddard-Kent-Olive paper observed was that there is an induced, in this situation, you have an induced action of diff S1 here, which So this is a completely new representation of diff S1, which you get by, so to speak, quotienting out a representation you had there from one you had there. And the paper proved that all the representations that are allowed by the found unitarity conditions arise in that way. And that was very important for creating lots of explicit models. But actually, I'm interested in it for a slightly different reason. I really will stop in a second. A very interesting point arises. In fact, in the Fagan-Fuchs paper, you only needed to consider the case where G, well, in fact, what they did was the following. They observed that the classification of these positive energy irreducible representations was precisely the same as the classification of complex line bundles with Hermitian structure on the circle with a connection. So in other words, you just take a line bundle on the circle. So you take an interval across complex numbers and you stick the ends together by some complex number. And the complex number should have modulus 1. And that's, you then consider the group of automorphisms of that bundle. And that's a group, a kind of twisted loop group. And you take its most obvious representation, its basic representation, and for a generic choice of the line bundle, you get an irreducible representation of diff S1 arising on it. It remains irreducible under diff S1, but for in complicated array of circumstances which they worked out, the representation decomposes and they determined the decomposition completely. Anyway, that was all worked out. But it leads to a sort of higher level problem, because what I didn't have time to say in my talk, alas, was sort of meant to be slightly implicit in this C. This central extension, which seems to be about groups of things which are maps from something one-dimensional, it's actually a transgression of something which goes right up to dimension 4. The anomaly in diff S1 represents itself in the fact that you get a projective Hilbert space associated to a circle rather than a Hilbert space. When you move up to a surface, you get a line. When you move one step up, you get a category, and so on. So there's a structure of what's nowadays called a topological field theory, which is associated to this picture. The central charge is the sort of lowest level of some four-dimensional topological field theory. Now, there exist, for topological reasons, really just two topological field theories in 4 dimensions that are of interest. So they've each got to give a number to a closed 4-manifold. And basically, there are just 2 possible numbers. There's the signature and the Euler number. They correspond to the 2 interesting 4-dimensional cohomology classes of the classifying space of more or less any D group. The Virasoro algebra appears to be connected with the Euler class, but the central extensions and loop groups are all connected with the signature operator, or possibly the Dirac operator if you put a bit more structure in, spin structures and things. And that's a puzzle, you see. Why do they somehow come out to be the same? Well, there are lots of reasons, but in the end, it comes down to this surprising Sugawara theorem, which tells you that the action of this outer automorphism group on the Hilbert space is absolutely forced by the conformal field theory structure. And there's really that somehow one of these theories determines the other very rigidly, and you can interpret that as a sort of philosophical point of view on the Fagan-Fuchs theorem. Anyway, it's time for me to stop, so I have to stop now.